So immediately after I put up your grades, I posted the keys to the homework assignments here. Chapter 2, sections 1, 2, and 3. You will notice one problem randomly selected to be graded out of 5, and then everything else examined for completeness. But the keys are complete. All of the problems are on them. If you've still got questions about what I was looking for or how I graded something, please come talk to me. Be glad to discuss both the grading and what you gave me versus what I was expecting at any point in time. Meanwhile, I want to extend the ideas we were dealing with limits, and especially when can I just plug in? Because that's really the best kind of a limit. If I can just stick the number in, I'm good to go, and that's the best idea. And really, that's a way of comparing the value at a, f of a, and the limit as x approaches a of f of x. And these two are independent of one another. Whenever we want, we can draw graphs. Take a look on page 115, and you'll see such a picture with all sorts of holes and odd behaviors going on here. There are plenty of places where the limit and the value don't line up and don't match. So, I like this idea of them matching. I like this idea of them lining up. If my function is nice enough, that's a good thing. So we had two examples. There were two types of functions that I've already given you, where we know we can just plug in. What are those two types of functions? If f of x is a or fill in the blank, then I can just plug in instead of doing the limit. We wrote it down explicitly. Yes, ma'am. Okay. And polynomials are powers of x, whole number powers, added, subtracted, maybe multiplied by numbers, things like, x squared plus 2x. Or a rational function. And the rational function is polynomial over polynomial. As long as I get a valid answer. In other words, when we plug in, and plugging in works. If I get 7 over 0, I can't do anything with that. So really, these are the ideal kinds of functions I want. I want functions that behave like these. So let me see if I can nail down when this is going to work. I have this limit over here on the left, the limit of x approaching a of f of x. I have f of a. Really, I want three things to happen. I want the limit to exist. If I have something that looks like this, the limit doesn't exist because the limit from the left and the limit from the right don't match up. I want f of a to exist. I want there to be an actual dot there. If there's an open circle or an asymptote or something else, then I have a problem. Then I want those two things to match. I'm going to call this idea continuous. A function is continuous at the point x equals a if, 1, the limit as x approaches a of f of x exists, 2, f of a exists, and 3, these two things match. But all three of these must be true in order for our function to be continuous at a particular dot, whatever x value we're looking at. If I go back to that picture on page 115, we can actually find an x value for each of these three conditions to be broken. So let's take a look at page 115 again. Here's our picture. Okay. Let's consider what's going on at x equals 1. So, do I have all three of my conditions holding at x equals 1? Okay, then which one's broken? Because I have a limit as I come in from the left or as I come in from the right, we're going to the same y value, but there's no dot there. There's an open circle. So there's no f of a. Without an f of a, I don't have the second condition. I'm done. As soon as one of them is broken, I'm out. What about x equals 3? Yes. All three of our conditions work there? At x equals 3. Then what's broken, Caden? They don't approach the same y value. So while I do have a limit from the left and I have a limit from the right, they don't match, so I don't have an overall limit. So my first condition is actually the one that fails. Even though I do have a value, the second condition works, I don't have a limit because the limit from the left is not the same as the limit from the right. So condition 1 fails here. Condition 2 failed here. What about at x equals 5? Which one's broken, Alina? The second one. Why? The second one says f of a exists, right? Do I have a dot above 5 somewhere? Okay, yeah, it's up here. But the first condition works. They approach the same y value from the left side as the right side. So I have a limit. I have a dot, but they don't match. So it's the third condition that fails here. I have condition 1, I have a limit. Of condition 2, I have a value, but I didn't plug the hole. So condition 3 fails. Each of these are called discontinuities, a place where my function is not continuous. 1, 3, and 5. But everywhere else on this picture, if we pick any other x value, say 2, as I get closer and closer to 2, from either side, I'm going to the same y value. There's no hole, so there's a dot above 2, and that dot lines up with my limit. So I need to be able to match all three of these conditions. Originally, when discussing the idea of a function being continuous, Newton himself simply said that we can draw it without lifting our pen from the page. And that matches our three different ideas, right? If I don't have a limit, then somewhere I'm going to have something from the left and something from the right miss each other. Or maybe I'm going to have one that goes back and back and back and forth and never settles down, and then I have to pick up my pen to draw the next part. So if my limit fails to exist, I have to lift my pen off the page. If my value doesn't exist, I have to jump over that x value. Whether that's because of an asymptote or a hole, I have to jump over it. And if the two don't match, that means I've combined these two errors in some fashion. A function that is continuous is smooth, with no holes, no jumps, no gaps. Visually, I like Newton's idea that I draw this without lifting my pen from the page, but that really does oversimplify it. Questions? That's from a visual. So how about formulaically? How can I tell if instead of looking at a graph, I'm looking at an equation? Here is a rational function. I already know that rational functions are nice when I can plug in and it works. So what happens if I just start looking at where can I plug in numbers? Where is this going to get messed up? At 2. If I plug in x equals 2, I'm dividing by 0. So I know f of 2 is undefined. F cannot be continuous at 2. Now, the real question then becomes, is there anywhere else that this might get messed up? And then it becomes a question of thinking about what the function can be reduced to, if it can. Remember, we said if we could replace the function with something else, then we could go ahead and plug in. Can I simplify that at all? How, Jack? Aha. You'll notice I did not put an equal sign here. The reason I didn't put an equal sign is because the thing on the left is undefined at 2. The thing on the right isn't. I know that I'm being pedantic and a little bit of a pain in the ass here. If you put an equal sign, I'm not going to yell, but I want you to know those are really different things because the thing on the left has a different domain than the thing on the right. This is defined everywhere. This isn't defined at 2. And that means that everywhere except 2, my graph looks like this. This is defined everywhere, which means f of x is defined for all values of x other than 2, because it works out to be this. And that's a polynomial. What do we know about polynomials? I can just plug in. So that's the only place this function is messed up. We will find it is often easier, instead of asking where is a function continuous, to ask where is it not continuous. Because not being continuous is a matter of finding out where you don't have a limit. Where is your limit broken? Where is your value broken? Or where are these things misaligned? Questions? Here is a piecewise defined function. My function is defined by 2 different formulas on 2 different parts of the x-axis. When x is not 2, I'm going to use the same formula we used up above. And I know that works. But when I plug in 2, I'll switch to the other formula. And I'll just get out 1. Is this continuous at 2? I know it's continuous everywhere else because this is perfectly fine for x not equal to 2. So the only place where this could now be screwed up is still at 2. Have I fixed the problem I had with f? Jack, you're shaking your head. Tell me why.
Because it's 1 at 2, so you still have to pick up. I know you said it's oversimplifying, but you still have to pick up and draw. Is that the same?
It's not the same as what?
X squared minus x. The rest of the.
Okay, so how do I check that? Remember, my definition has 3 parts to it. A function is continuous at a point if 3 things occur, right? If I have a value, a limit, and they match. Do I have a value at x equals 2? Does g of 2 exist? Yeah, right there. G of 2 is 1. What about the limit as x approaches 2 of g of x? How do we know? When we're approaching 2, that means we're not using 2, right? We're using all the other parts. We're looking at what happens as we come in from either side. So I'm not using 2. That means I'm using this function. I'm not using 2 itself. But what did we do with that function? When we were thinking about f.
We simplify it to f of one.
Because if I do just plug in right here, I get 0 over 0, which is an indeterminate. And as soon as I see an indeterminate, my brain goes, I should try and fix this. And in our case, we can fix this. We can resolve this. We can determine it. And then what happens to this? That's a polynomial. I can plug in. So when I plug in, I get 3. And Jack, you're absolutely right. I had to pick up my pen. Because as I'm drawing the graph, my y-axis should be going to 3. But we're down here at 1. Oops. So I have a limit. So in spite of the fact that I have a limit and I have a value, I didn't plug the hole. The graph of g of x should look like that. That's an open circle. I just drew it too small for you all to see. See my problem? I have a limit, perfectly defined at 3. I have a value, but they don't match up. I tried to plug the hole and I missed. How could I fix this? How could I make a new function that is continuous? What change could I make to g of x? To fix that problem? Move what? I want to move something, but what's the thing I should move? I'll define a new function, h of x. I need to fill in this spot so that I fix it, so that I make the limit and the value match. What's the right thing to put here? It should be 3. Because now the limit exists. The limit is 3. The value exists. The value is 3. Since those two match up, I plug the hole. I'm good to go. In a very real sense, we've gotten rid of the discontinuity. We've added something to our function and made the discontinuity go away. A hole in the graph is a removable discontinuity if there's a way to plug the hole. Sometimes there isn't a way to fix it. Here's an example. Where is this function not continuous? At x equals 0. And if you graph this function, what do you see going on in the picture at 0? There is a vertical asymptote. And what's more, that vertical asymptote at 0 means we actually have a limit at 0. The limit as x approaches 0 of 1 over x squared is infinity. Because this keeps going up and up and up and up and never stops. But infinity is not a number. It's a concept. It's an idea. There are ways to treat infinity as a number. We'll do that way past this course. But for now, infinity is not a number. It's an idea. So there's no place for me to plug the hole. No matter what value I plug in to be the y value at 0, if I plug in a number, I haven't gone up high enough. I don't care what the biggest number is you can think of. Infinity is bigger than that. And that's the problem. There's no way around this. It's not removable. It's baked into the function. It's essential to the function. So discontinuities really come in two flavors. Holes we can plug, and asymptotes, or jumps that we can't. Or jumps. I'm going to define for you a new function. Floor of x, also called greatest integer. And it's sometimes written with half brackets. See how it's got the feet on the bracket, but not the top? The floor, not the ceiling. Somebody pick a number that is not a whole number. Okay, I want you to give me the integer, the whole number, that is as big as it can possibly be while still being less than 1.5. And if I picked 1.7, I'd still get 1. And I picked 1.83, I'd still get 1. I picked 1.23456, it's still going to give me 1, right? So for every value between 1 and 2, I should get 1. But as soon as I hit 2, I should jump up, shouldn't I? This function, when I graph it, has a very interesting picture. We just said between 1 and everything up to 2, I should get 1. But as soon as I hit 2, I should jump up. And between 2 and 3, I should get 2. Everything between 0 and 1 should give me the value 0. Everything between -1 and 0 should give me the value -1. This round down function gives you the number, the whole number, under the floor. If I round it up, we'd call it the ceiling function. This is called a step function. I hope the reason for that is fairly obvious. Looks like a set of steps. You've seen these. Shipping and handling. Postage. If you go to ship a package, anything under 1 pound, we charge this much. But as soon as you get over a pound, we jump up the price. As soon as you get over 3 pounds, we jump up the price again. Those jumps are unavoidable. They're baked into the function. They're not fixable or removable like our holes were. This picture appears at the bottom of page 116 in the textbook. Questions? Sometimes our continuity is unfortunately a little more complicated than what we've just been doing. What's the graph of the square root of x look like? If you don't know, you should take out your calculator, graph me the square root of x. That one's x squared. That one's the absolute value. What's the square root of x? Out come the calculator, draw me a picture. This is where the math dance comes into vogue, right? Y equals x squared, y equals absolute value, as we dance way around looking like the YMCA. Ms. Beninati has a mug with all of those on them. Aha, we get an arch, but there's only one side to that picture. When I graph the square root of x, I get a graph looks like this. So here's a real legitimate question for you. Is this function continuous at 0? If I go through the definition, the first thing in the definition says, what is the limit as we approach 0? Now I have a problem. Because when I'm coming from the right, that makes perfect sense. But when I'm coming from the left, there's no f of x there. I don't have a limit at 0. Because I don't have one from both sides. But this function only exists on one side. Should I really use a limit that's got two sides? Maybe I should switch that up. And I should talk about only using the limit from one side. We have one-sided limits. Only come from the right, only come from the left. I can do the same thing with continuity. I can have one-sided continuity. If I only look at being continuous from the right, then this works. If I think about only working from the right, then this works. The limit as we approach from the right is 0. The value when we plug in 0 is 0. And those match. This is continuous from the right, as opposed to continuous on both sides. I do the same thing for from the left. If I replace the limit with the limit from the right, I have continuous from the right side. If I replace the limit with limit from the left, I have continuous on the left side. This is particularly useful when dealing with functions whose domains are restricted. So all I do is I change whether I've got a little plus or a minus above my limit at A. If I have an interval from A to B, I can talk about being continuous on that interval. If I include the point on the end at the left, then I want to be continuous from the right. If I include the point on the end of the right, I want to be continuous from the left. But it means there are no discontinuities at any point inside that interval. So I can talk about continuity as a single point idea, but I can also kind of spread it out to cover whole pieces of the x-axis. So if I'm using a closed interval like A and B, and A and B are both included, then I want A to be continuous from the right, and I want B to be continuous from the left. And I want it to be continuous on both sides, everywhere in the middle. Questions? My favorite thing about continuity is that all of the algebra I like to do doesn't F it up. If I have two functions that are continuous and I add them, the resulting sum is still continuous at whatever point I'm at. So is the difference, the product, C times f of x, where C is a constant, and f of x over g of x, as long as I'm not dividing by zero, because dividing by zero blows everything up. This means that almost every single algebraic, trigonometric, exponential, whole piles of algebraic functions we like to use, they're continuous wherever they are defined. Page 120. The following types of functions are continuous at every number in their domain. Polynomials. Polynomials are defined everywhere, so they're continuous everywhere. Rational functions. As long as I'm not dividing by zero, I can just plug in. Roots, no problem. Trig, inverse trig, exponentials, logarithms, I want you to imagine you were asked to do this crazy mother of a limit, or figure out where this thing is going on. Well, this is continuous. I need to know about the function pieces that go in here. ln is good as long as x is bigger than 0. Inverse tangent is good everywhere. X squared minus 1 is on the bottom. I'm not allowed to divide by 0. Where's the bottom 0? Or, but I already threw out -1 because ln threw out everything that was not bigger than 0. So I really don't have to worry about 1. So I go between 0 and 1, or I go anything bigger than 1. And this is continuous everywhere there. It also means that I can evaluate all of those types of functions just by plugging in. And that saves me a lot of work when I'm trying to do limits. It gets better. I can put a continuous function inside another continuous function. F of x is continuous at some point A. And g of x isn't continuous at A this time. It's continuous at what comes out of F. Then the composition G circle, G of F of x, is continuous at A. Now remember, this composition idea doing one of them after the other. So I applied F here, applied G here. If I go straight from here to here, we're going to call that G of F. Composition like this preserves continuity as well. If I take a continuous function, take something out of that, plug it into another function, like sine of x squared, or square root of x cubed plus 4x. Hell, let's go crazy. Square root of cosine of x. Cosine is continuous everywhere. It's a trig function. It's continuous wherever it's defined, and cosine is defined everywhere. Square roots are good wherever the thing is positive. So square root of cosine of x is good wherever cosine is positive. Again, this is going to allow me to evaluate limits fairly easily, in my opinion, because now I can just say, oh, I can plug in. I can move to the inside and plug in. I can move to the inside and plug in no matter how many layers I need to go. Questions? The other day, we were working on our calculators to find where two curves crossed. One of the things we do is just plug it in and say, hey, go. What's the calculator actually doing? Calculator is actually using continuity. There's a really nice result that comes out of the idea of a function being continuous. The intermediate value theorem. The intermediate value theorem requires me to have a function that is continuous on an interval. So I'm going to start with the hypotheses of this theorem. Suppose f of x is continuous on some interval from a to b, and that f of a is not the same as f of b. Now, before I write down the conclusion, if these things are true, then something nice happens. I want you to make a picture for me. F of A and F of B have two different y values. So you have to decide for me in this picture. Is F of A higher than or lower than F of B? Do we go like this? Or do we go like this? Doesn't matter to me. You write down two dots. One for F of A, one for F of B. And all I care is that they are not the same. I don't care which one's higher, which one's lower. Chris, which one did you make higher? Okay, so in your picture, F of A is up here, and F of B is down here. I've drawn them as both positive. They don't have to be both positive. One of them could be negative. It doesn't matter. Here's the statement that goes with this. If you pick any value between these two, I'm going to call it n. Then there is some x value between A and B that gets that y value. Now, this sounds insane. So here's what I want you to do. On your picture, pick a value between f of A and f of B on the y-axis and make a mark. I don't care if it's close to f of A or close to f of B or right in the middle. It doesn't matter. Pick a spot and call that n. And then draw a horizontal line at that height. You with me so far? Now I want you to connect the dots you made. Your dot f of A, your dot f of B. Connect those in a continuous function. You've got to draw. You can't go back and forth from left to right. You have to go only one way. You can go up or down as much as you want, but you have to connect f of A to f of B. Aren't you going to cross that blue line somewhere? I don't know where, but somewhere between A and B, you've got to cross that line. When you draw your function, maybe it crosses more than once. But this value right here, that's my value C. The intermediate value theorem says that because f is continuous, it must hit every value in between, intermediate from f of A to f of B, somewhere between intermediate A and B. You must always fill in all of the vertical space unless you jump over it, right? And if you jump over it, you're not continuous. This is how your calculator finds out where two things cross. It takes the first thing minus the second thing. And it says, hey, this is positive, now it's negative. If I go from positive to negative, what had to happen in the middle? If I have to go from positive to negative, somewhere in the middle, I had to hit 0, didn't I? And so I go, oh, I went too far on negative, now let's back up a bit. I went too far on positive. Back, go forward, I'm on negative, back, and I narrow in until I find out where those things, their difference is 0, they must be equal to each other. We can make some remarkable pictures that use the intermediate value theorem. One of those assignments is in our homework for this section. Draw several more of these pictures, they will help. I will see you all on Wednesday. Have a wonderful rest of your day.